Let's look at an intertemporal consumption investment model. This kind of model is meant to capture the trade-off between consumption in the present and consumption in the future, i.e. present investment. We're going to assume a continuous time and an infinite horizon, which is arguably the easiest setting to solve. One may also assume discrete time or finite horizon, but finite horizon in particular implies some complications which we do not have to deal with in an infinite horizon. Models of this kind are usually solved using either Pontryagin maximum principle or Hamilton-Jacobi-Bellman equations, and we will use the latter method in this video. To follow along with the math in this video, you should be familiar with this method. Let's look at how we build the model. We have a utility function given by this expression. Ct is consumption, and we raise it to 1 minus gamma, where gamma is a parameter in the open unit interval. Gamma determines the curvature of the utility function and hence the marginal utility. If gamma is close to 0, we have an almost linear utility function, basically looking like this. While if gamma is close to 1, the utility function will be very curved, looking more like this. So the higher gamma, the more will marginal utility decrease in consumption. Next, we have a discount function given by this expression. This is a standard exponential discount function where rho is the discount rate. And of course, we need to specify the dynamics of the state variable, which is wealth. So we have the time derivative of wealth equals to the interest rate R times Wt minus Ct. This simply means that at each point in time, our wealth grows at a rate R, but we also subtract the rate of consumption. So basically, the way to think about this is that in every new period, we first earn interest on how much wealth we bring into this period, and then we subtract the amount of money that we spend on consumption. And notice here that we're assuming that the price of consumption is always equal to 1. So there is an implicit Pt, which is equal to 1 here, multiplied by the Ct. Before solving the model, I just want to mention the basic mechanisms that this model captures. First, we have the fact that the consumer discounts future consumption, and this provides an incentive to consume right now rather than to invest in the future for later consumption. On the other hand, the consumer receives interest on savings, which provides an incentive to save rather than consume right now. So we have these two different incentives that push in different directions. One of them pushes towards consumption right now, and the other pushes towards consumption later. And the relative strength of these two forces, so to speak, will determine the behavior of the consumer. The third mechanism is the fact that we have decreasing marginal utility in the utility function. And this provides an incentive to smooth consumption over the whole time interval rather than to consume in a specific period only. If there was no decreasing marginal utility, that is, if the utility function was linear, then we could put all consumption in one specific time period and have nothing in all the other time periods. And it will make no difference to the utility, to the total utility. However, because marginal utility is decreasing, there's an incentive to smooth consumption over the whole planning horizon. And notice that the curvature on its own doesn't tell us anything about in which period we should put all consumption. If we have linear utility functions, there's no incentive to smooth, so we can put all consumption in one period, but it doesn't tell us which one. However, because we are impatient because we discount future consumptions. These two effects together provide an incentive to consume right now rather than to wait for later. But of course, the higher the curvature, the more we want to smooth, so the more we want to save. This is how we formally represent the problem. We maximize by setting Ct over the whole time interval from 0 to infinity. And what we maximize is the integral over the whole time interval of the utility function discounted. So we maximize the stream of discounted utilities, all discounted back to time 0. We do this subject to the wealth process and the initial constraint of wealth, W bar, which is the initial amount of money that we bring into the problem. Also recall that we have the value function, which is an important object in the Hamilton-Jacobi-Bellman method for solving these kinds of problems. This is defined as the stream of discounted utilities that we obtain when we employ the optimal strategy. So this Ct star is the path that we want to find in solving the problem, and we define the value function as the stream of discounted utilities that we obtain when we use that so far unknown path. So let's solve the problem. First step is to set up the Hamilton-Jacobi-Bellman equation, which looks like this. We have the utility function, we have the discount rate times the value function, and we have the derivative of the value function times the dynamics, the wealth dynamics. This is a strictly concave function in C. We know that because the utility function is strictly concave and this term over here is linear. Strictly concave plus linear equals strictly concave. So all we have to do to find the maximum of this expression with respect to C is to take the first order derivative and set it to 0. We can then solve for C star, which is this expression. Notice that C star depends on the value function. We can substitute it back into the Hamilton-Jacobi-Bellman equation to obtain this rather complicated looking expression. Next, we need a conjecture on the value function. And for this model, the correct conjecture is this. So the value function is some parameter, which I call a to the power of minus gamma, times w to the power of 1 minus gamma divided by 1 minus gamma. So the value function has the same power as the utility function, which is not a coincidence. And you can prove this result using, for instance, symmetry. Using this form for the value function, the optimal consumption C star, which we derived previously, simplifies to this expression. It's simply the parameter A times wealth. So all we have to do to find the optimal path is to find the parameter A. Using the conjecture, the Hamilton-Jacobi-Bellman equation reduces to this term, to this expression. And notice that we have three terms here, this, and this, and all three are multiplied by A to the power of minus gamma times W to the power of 1 minus gamma. So we can divide by that. And then we can also multiply by 1 minus gamma to get rid of the denominators here and here. Doing that, we get this expression, and we can now easily solve for A using by rearranging terms, and we get this expression for A. And remember that C star equals A times W, which means that we have now found C star, we have found the optimal consumption path. So all you have to do now is to find the wealth path. Doing that, we substitute C star into the wealth dynamics to get the differential equation W dot equals a constant, R minus rho divided by gamma times W. And we can easily solve that using the initial condition W0 equals W bar. And we get this expression, we get an exponential. So we have solved the problem. Let's look at some properties of the solution. Consumption is a constant fraction of wealth. The fraction is equal to this expression. So at each point in time, the consumer looks at how much wealth he has and then subtracts a fraction of that wealth for consumption. And the fraction is always the same in every time period. Wealth grows or shrinks exponentially. So it will either grow like this forever or decrease like this and converge towards zero. Which one we get depends on the relative sizes of rho and r. It depends on the sign of the expression r minus rho divided by gamma. So if r is greater than rho, wealth will grow forever. If r is smaller than rho, wealth will decrease forever. If r is equal to rho, we get a constant development like this. Wealth never changes because in this case the consumer always subtracts exactly the same amount he gets in interest. So every period he consumes up his interest income so that his savings remain constant. Now recall that r and rho are the interest rate and the discount rate. If the interest rate is greater than the discount rate, wealth will increase. It's because interest is so large that we have an incentive to save. On the other hand, if rho is very large, we are very impatient. We discount future events a lot, which means that the interest rate we receive on saving is not enough to make us want to save more. We want to consume now instead. Finally, notice that consumption decreases in the curvature gamma. Now, this is a very simple model, and there are many extensions. For instance, we can have a finite planning horizon. This complicates solving the model. We can have other forms of utility functions, for instance, exponential, logarithmic, and quadratic. We can have two or more consumers withdrawing money from the same fund. This would make our model a kind of game theory model. We can have random returns to investment, using, for example, a Brownian motion or a Poisson process to model the randomness of the returns. This is generally known as a Merton model. And we can have non-exponential discounting, which makes the model slightly more realistic, but also much more complicated to solve.